Here we go. Can you see that in the corner there? This one right here. So if you have cosine alpha times cosine beta, it turns into cosine alpha plus beta plus cosine alpha minus beta over 2. Split it into two fractions, then you have two individual cosines that integrate easily. Yeah? Yep. All right. Pretty nice, huh? Pretty nice, this Green's theorem. Take a look at this. So remember, I mean, Green's theorem applies both ways, right? You can go from a line integral to a double integral, right? And then if you're talking about areas, you can go from a double integral to a line integral. This one, I'm asking you to find FDR. This is what I started class with, right? Something like this. It's just a different example. FDR, here's my field, okay, ugly field. And I'm giving you that the C that we're going to do this line integral on is a triangle. I'm going to draw the triangle. Goes from 0, 0 to 2, 6 to 2, 0 back to the origin. Notice the way I stated the problem. We're going from 0, 0 to 2, 6 to 2, 0 back to 0, 0. That means my orientation of my path is what? Clockwise, which is negative orientation, right? Negative orientation. So what happens when we reverse the direction? Our answer is just going to change signs. We just need to basically do a negative in front of this, right? So this should be equal to the negative, see if you follow this. This is the notation we use. See, I'm trying to find this, right? And I'm given that C here. By the way, this should have a, this should have this here like this, right? And should I put anything else? Yeah, the arrow, because C is being traversed that way, right? I didn't put that in there. It should be there. We're traversing C in the clockwise. Now, I technically didn't need the arrow in there because it's implied in my wording here, but that just kind of like stresses again that this is negative orientation. So if I want to do this integral, do you all agree and understand that this is the same as the negative of this integral, which basically means I'm doing the opposite orientation of C. This negative C means the opposite direction. And notice that my circle here now doesn't have the arrow on it. So the integral with the negative orientation turns into the negative of the positive orientation. Fair? Fair? All right, now this, by Green's theorem, should be, negative comes with us, negative of the double integral over d of the partial of q with respect to x minus the partial of p with respect to y dA. And I'm hoping that partial q with respect to x and partial p with respect to y are good. I also need to talk a little bit about the region here, D. Right, D here. That's a pretty nice region, isn't it? Good old-fashioned type 1 region when we were doing double integrals, so we should be able to tackle that pretty straightforward. Let's get this, though. Partial with respect to q, partial q with respect to x is partial q with respect to x, 2x, what else? Plus 2y, what? I didn't hear you. Cosine x, okay, good. So we're taking derivative of that with respect to x, derivative of this with respect to x, the 2y comes, derivative of sine is cosine. All right, take that, subtract from that what? Partial of p with respect to y. What's partial of p with respect to y? 2y cosine x. Hey, it's almost like they made this problem for us to work out, huh? They did, right? They wanted this to cancel out because they want this to be nice for you, right? Yeah, I just took this out of the book. Yeah. Oh, no, what you want is one where it comes out to be a constant, right? Because then it's just the area of that, and then you're really, really nice. All right, questions? We've now taken this is actually work. This is the work integral. So we're trying to find the work done moving an object along this path through this vector field. That's what we're doing, and it's turning out to be this double integral. So now let's do this region. I'm going to do type 1, good old-fashioned type 1 region from when we first started double integrals. My x here is bounded between 0 and 2, and my y is bounded between, well, that's a line. What is it? 3x, right? Slope is rise 6, run 2. Slope of that line is 3x, or 3. And then it hits through the y-intercept is at 0, so just the equation of that line is 3x. So it goes from 0 to 3x. There it is. So this now becomes negative integral 0 to 2, integral 0 to 3x, 2x, dy dx. And let's see, did I do it on the computer? Because I don't think I did, yeah. Do y'all want to keep going? Finish it? Yeah, finish it, okay, we'll finish it. All right, let me put it up here so you can see it. Double integral, let's see, 0 to 2, 0 to 3x. We're integrating 2x dy dx. So first thing I do is integrate with respect to y, right? So that just turns into 2xy. And I'm evaluating from y equals 0 to 3x. Whatever that all turns out to be, I'm going to still have to integrate with respect to x. This is the integral from 0 to 2. Okay, now plug in 3x for y, you get 6x squared. And then you plug in 0 for y and it kills everything off. So we're integrating that with respect to x. That's just 3x squared from 0 to 2. And so you get 12. 3x, oh, 3x, yeah, 3x cubed. No, not 3x cubed. What is it? What am I doing? 2x cubed. That's here? You didn't see it? Pay attention, please. This has been a day, I'm telling you, this has been a day. In my 13-14, I teach 13-14 class. In my 13-14 class, I made 4 mistakes. And they were things, stupid things like, we had a decimal 0.0012 and I put 0.012. Like things like just, I think my mind was a little checked out today. No excuses. At least you're paying attention. Okay, 2x cubed, and I'm evaluating from 0 to 2. 8, 16, negative 16? Yes. There we go. Pardon? On the first try. Yeah. What is negative work? Well, it's kind of a relative thing, right? It's like a directional thing.
What would it mean in this scenario?
What would it mean in this scenario?
We said we're trying to calculate the work done by the curve through the vector field.
Well, okay, what if I change the direction around, right?
Oh, okay.
Then the work's positive, right? So for every positive work, you could look at, there's just, the other direction would just be the negative of it. That's all it is. Is that enough? Is that satisfying? Okay. That's why I'm saying direct. It's just about direction. You pull something in this direction, you say that's positive work, then the other way would have been negative work. You know?
And I just always look at work as force times distance, so.
Yeah.
And,
I hear you, but your distance,
yeah, no, I'm
your
good.
displacement, right? It's a displacement vector.
I made a click in my head, so I'm good.
All right, we have last thing here in Green's theorem, all right? Every region that we've been looking at, right, with Green's theorem, every curve we've had with Green's theorem has enclosed a simple region. It's been simple. There's never been any holes in it, right? So what if we have something like this? What if we have this region D that's actually enclosed by an outer loop and then this inner loop, you know, that piece has been taken out? Like, can we somehow still use Green's theorem? Is it possible, right? So what I'd like for you to do is consider two different paths that I'm going to create, okay? I'm going to call one path C1 and the other one C2. C1 is going to go around, and that is going to be positive orientation, right? Because the D is, but remember I told you if you walk along, positive orientation means you want your region down to your left. So do y'all see if you're walking along C1, you've got positive orientation? And then if I'm walking along C2, is it positive orientation? No, right? It's negative. Because if I walk around here, right, where's the region? It's to my left, right? But I'm going clockwise instead of counterclockwise, right? So I'm going to draw it this way. You all with me? Just let me draw it this way. C1 goes counterclockwise, C2 goes clockwise. Now what I'd like to do is split the region D anywhere you want. On this side somewhere, split it, and over here, split it. So now I've created two new regions, D1 and D2, right? Yeah? Now I'm going to create two new paths. One path is going to be called E1. It's going to be the one that goes around D1. And it's going to go in positive orientation, right? And then E2 is the path that goes around D2. And look at it. It goes in its positive orientation as well, isn't it? Notice that if I were to move along E1 and E2, in other words, imagine a line integral. Imagine we did a line integral that went along E1 and then another line integral that went along E2, two different line integrals. What would happen when you go across this and this here, and then when you go do this line integral, what happens when you go here and here? What happens? They should cancel each other out. Like you were just saying, it's like work the opposite direction. One's positive, one's negative, right? So on this little strip here, on these two little strips, in one direction or the other direction, this is basically gone, and this is gone, right? So those two parts kill each other off. So what you have is that the original double integral, this is Green's theorem but backwards. The double integral over that big region D that had the hole in it, right? What it is the double integral over the two pieces we cut it into, right? D1 and D2. We're allowed to split this into two separate regions because we did that way early when we learned about double integrals. We could split it up and union the two. Okay, so that's equal to this just by properties, but then that is just the same as going and adding up the line integrals along those two paths. And you have to, the thing that you have to convince yourself of is that when you do the E1 and the E2, because the middle parts cancel, you're basically left with the C1 and C2. And so that's why you get the final result that the double integral over D is just the line integral over C1 plus the line integral over C2. That's it. That's the result. So I'd like to just put one more thing here just so we're clear. Give me a region, cut a hole, call that D. Take a path that goes along the outside C1 that goes in positive orientation. Then take another path that goes this way, C2. right? They have to be in opposite directions. If C2 goes that way as well, this doesn't hold. They had to be opposite so that those parts would cancel out with each other. Yes?
How would you find a line function that realistically maps that type of shape out?
How would you find a what?
Like a line function or...
Well, you could just take, take this here. I'm going to define a region here for you. There.
I know for the easy ones.
Oh.
For like the complicated...
Oh, well, this is just general. This is just to be general. I mean, you saw that epicycloid, right? Imagine I take the epicycloid and then take out from it some ellipse. Then it would look kind of more chaotic to you, yes? Is that satisfying? I mean, you can come up with things that would draw this, right? We're trying to be like abstract with it. Okay, so if we have this region D, we've got a curve going in the positive orientation around the outside and another curve, C2, going negative orientation on the inside. Then the double integral over D of Green's theorem, partial Q with respect to X minus partial P with respect to Y with respect to area, all of that should just be the sum of the two line integrals, C1 and C2 respectively. Okay? I want you to take a minute to read this. I'm about to use what I just showed you. I'm about to use it. But I want you to appreciate this problem first. For those of you who are like geared more towards like math major type stuff, I know there's a few of you who are thinking math major. This is more of like a math major type problem. Not so much because it has to do with the way we're going to tackle the problem, the way we're going to address it. Does anyone have any comments on this? Anything that's glaring, that's like different and very strange? What's different about this problem compared to any other problem I've given you up to this point? C. What's wrong with C? C has to be what? Any closed path that encloses the origin. How many paths can you think of that are closed that enclose the origin? Infinitely many. So how in the world are we supposed to show that no matter what curve we ever draw, as long as the origin is inside of it, that integral is going to give me 2 pi? I'd have to like evaluate every integral, right? Every path, which is impossible, right? What's that? Well, it's important to us, right? This says it has to have the origin in the path, right?
So it could be infinitesimally small, just the origin.
That's one path, yes. It could be an infinitesimally small path. That would be one path. We have to show that would give us 2 pi if we did this. But then it has to be any other path we could come up with that would also enclose the origin. So we could, like right now, pick a path. As long as the origin's in it, we could show that it's 2 pi. We could try at least, right? But again, that would just be one example. So how do we cover all examples? Do you understand the magnitude of what they're asking? Like, this is not easy, not straightforward.
Is it like how we approach the limit?
Like a limit or something? I'm not going to say no, because maybe there's a way we could do it with the limit. But I think, so look, I want to show this to you because this is one of those things where I really feel like you would have to sit down with this for maybe ever and not come up with it, because it's a technique, it's an approach that I don't think is natural at all for anybody to do. All right? At all. So math majors, they have to see things like this because they need to know that they can think this far outside the box. All right? And the more you see it, the more comfortable you are trying things that don't seem like they're going to get you anywhere, all right? So may I proceed? Okay. If you were on this, no, don't do it. If you were thinking this in some way, Austin, you're kind of talking infinitesimal. You're on the right track, but not quite sure we'd be able to formulate it all together.
Double integral?
Double integral, yeah. Let me go. Yes? All right, here we go. Fundamental theorem. So here's what I'm going to do. I'm going to draw, okay? And what I'm going to do is I'm going to draw a curve that encloses the origin. Arbitrary. I'm going to call that C. Everybody happy so far? Does that C satisfy that? Yes? I need to show now that when I move along this curve, right, positive orientation, yeah, it's closed. There could be a circle up there, right? I need to show that my answer is 2 pi. But I don't have a parametric representation of that curve, do I? Because it's arbitrary. So now here's the big, like, whoa, why would you do that? What I'm going to do is I'm going to draw another curve, a second curve. And as long as the origin is inside this curve, not on the curve, so that this curve cannot cut through the origin. It has to enclose the origin, which means the origin has to be inside. Do you all agree, as long as the origin is in the curve, I should be able to come up with an infinitesimally small circle that fits inside of this? Right? So I'm going to choose, let's say, A greater than 0. I'm going to choose a positive number greater than 0 such that the circle x squared plus y squared equals a squared is inside C. I'm going to fit a circle of radius A into that curve. Nobody objects, I can do that? Everyone agrees I can? All right, so here it is. It's a little circle with radius A. Now, can you draw me A? How can you draw A? I mean, sorry, A. Let's call this one, I never called it anything. Let's call it C tilde. I could have called that C1 and C2, but I'm just going to use some different notation. That's C tilde. Can you draw C tilde for me? Can you give me the parametric representation of C tilde? So C tilde is x of t is, what did you say? A cosine t, and then y of t is a sine t. We all good? T is going to go between 0 and 2 pi. That will draw me C tilde, right? Why? Okay, so where is this going, right? Where in the world is this going? Big deal, I can draw that, right? What orientation is C tilde? The way I parametrized it over there. It's positive, right? It's positive orientation, which means it's going counterclockwise, right? Right now it's going counterclockwise. But I just showed you a theorem, didn't I? I just showed you something before this where we had that region. Let me put it over here. I'm going to do it off camera, but it's in our notes. We had this region D, didn't we? And we had one curve going across like that, C1. And then we had this curve in here, we called that C2, right? They were opposite orientations. And what we deduced was that the double integral over D, the whole thing of partial Q, with respect to x minus partial P with respect to y, dA, that's equal to the line integral over the closed curve C1 of P dx plus Q dy plus the line integral over C2 of P dx plus Q dy, right? That's what I just tried to convince you of, that you can basically take that region, do the double integral of this, and that becomes this. So do y'all see that that's almost what I have over there, except for what? C tilde is in the wrong direction, right? C tilde is in the wrong direction. Easy fix. Let's consider negative C tilde now. According to according to this, what do we have? We have that the line integral over what? C1 for us, what's C1 over here? C1 over there is what for us over here on the left? C, that, of P dx plus Q dy, right? Must, plus the line integral over what? Negative C tilde, right? Negative C tilde of P dx plus Q dy, right? Must be equal to this double integral, right? All right. Looks terrible, doesn't it? Doesn't this look terrible? Questions before I continue? All right. I want to figure out what this is right now. This is going to be the key to the rest of the problem, is figuring out what this is. So let's do these like scratch work. What's the partial of Q with respect to X? All right, so I'm asking you to think about this, right? Q, and differentiate that with respect to X. Quotient rule, right? Quotient rule. So derivative of the top, 1 times the bottom. People do quotient rule different ways. Depends on how they're taught, right? So we should all get the same thing, right? Minus derivative of the bottom one, 2x times the top, which is x. All of that over the bottom squared. That's our quotient rule, right? Let's clean it up. This is x squared plus y squared minus 2x squared all over x squared plus y squared, all of that quantity squared. One more line. What's that numerator? Negative x squared plus y squared, or y squared minus x squared, however you want to write it. I'm going to write it as y squared minus x squared all over x squared plus y squared, all that squared. Okay, that's the partial of Q with respect to x. Not good. Not looking good. Yes? Not looking good? What's the partial of P with respect to y? So take the partial of this with respect to y. So same thing, right? Quotient rule? What's the derivative of the top? Negative 1 times the bottom. Okay, minus derivative of the bottom. 2y times the top, right? All over the bottom squared. Yes, negative y. I'm telling you, math purgatory. It's going to be bad for me. So derivative of the top times the bottom minus derivative of the bottom times the top, which was negative y. And then clean that up. What does that clean up to be? Hey. Y squared minus x squared over x squared plus y squared squared. They're the same, right? They're the same. And because they're the same, when I subtract them, what do I get over here? 0. Okay? We're not done. But that is like a big deal. Because what that tells me now is this. Okay? Do you all understand? This is now 0. Okay? So, can I erase this yet? Can I erase this in here? You all right with me getting rid of this? Okay, so here's where we are. We have that this line integral over C of P dx plus Q dy plus the line integral over negative C tilde of P dx plus Q dy must equal 0, right? What's another way I could write this? Hold on, I want to move this to the other side. So couldn't I make that not negative tilde, c tilde anymore, and make that a negative here and change it to positive c tilde? So that could become minus integral over c tilde, but not change, I changed the direction, so it changed the sign of the line integral. Now move this integral to the other side, and we have the following very, very nice thing, which is that the line integral over c of p dx plus q dy must be equal to the line integral over c tilde of p dx plus q dy, which is telling us what? They're the same. That means the value of this line integral is the same as the value of that line integral. That's huge, because this I have a parametrization for, don't I? So if I can just do that line integral, whatever that answer is the answer for any curve. So let's do that line integral. Let's do this right here. Let's go find it. How do I calculate that? Well, I need a parametrization, don't I? For that curve c tilde. Do we have it? Yeah, there it is. So let's just do these. It's the integral from 0 to 2 pi. All right, this is going to be terrible, look terrible at least. Can you all tell me what p is? Where's mine? Careful, what's p? Then we'll do dx. What's p for us, though? It's that right there, right? That's p, but I need to plug in for x and y. I need to plug in these two. It's going to look horrible, but things are going to be beautiful at the end, all right? So I'm p, this is p, this is q. So p is going to be what? Negative y first on top. What's negative y? Negative a sine t over, okay, what's the denominator? X squared plus y squared. Not quite 1, almost 1. A squared. If you square this and square that and add it together, you can factor out an a squared, and then the sine squared and cosine squared turn into 1, right? Should I show it or no? No? Okay, so the bottom is just a squared, isn't it? Okay, that's p. Sorry, that's p. I'm not doing this. Doing this. So that's p. Now what's dx? Dx is the derivative of this right here, which is negative a sine t. All right, dt will come at the end. I now need to do this. Plus, what's q for us? Well, q is this one, isn't it? Replacing x with a cosine t over a squared again